All right, so we're going to start looking at how to find power series solutions for first order differential equations. Before we do that, I do want to remind us how to do this with like a linear integrating factor. So if I were to see something like this, I would say, okay, well, let mu be equal to E integral of 1 dx. Because there's a 1 here in front of my y. And so this is going to be e to the x. And so what this tells me is the derivative of mu times y must give me this here when I use product rule. And so that must be equal to this here, which is just 0. Well, e to the x, y would then be equal to some constant. If I integrate 0, it must be some constant. And so y must be c e to the negative x. So let's look and see how we would do this now with the new series solutions. What I need to know is I need to know that this is my form of my generic series for a power series. And when I take the derivative of that, let's write out a few terms. So we would have what? C0x to the 0, C1x to the 1, C2x squared, so on and so forth. When I take the derivative of that, this goes away. I end up getting C1 plus 2 C2 x to the 1, so on and so forth. So the way that I can write this is if this is my generic power series solution, what ends up happening is y prime, I can take the derivative just like I would a polynomial. The problem is, though, when I do that, I don't actually start at the 0, I start at the 1. So I have to refix my index. Otherwise, I'm going to have negative polynomials when I do this. So I'm going to have n times c to the n, x to the n minus 1. So again, I can't start this at 0 because then I'd have x to the negative 1. It's not a polynomial anymore. So when you take these derivatives and you take that n down, know that like your series actually starts at C1 now, x to the 0, right? So I need to make sure that I have that here. And you can go through and verify that these are the same thing. All right, so I need to then plug this in, y prime plus y equals 0. So that means this series plus this series must be equal to 0. Well, in order to combine these, I need them to have the same index and the same start. So I'm going to say k equals n minus 1 here. That means that n equals k plus 1. When n equals 1, k equals 0. And so this is going to be k equals 0 to infinity of k plus 1, ck plus 1, x to the k. Here, I'm just going to switch out all of my n's with my k's, and then I would have k equals 0 to infinity, ck, xk must be equal to 0. Well, it's just so nice that these end up having the exact same index, so that is so great. So I can write this as one series, k equals 0 to infinity. I'm going to go ahead and combine my coefficients here and factor out that x to the power of k. Now, what does this mean? Well, I have that this is equal to 0, So that means that it has to be 0x to the 0 plus 0x to the 1 plus 0x to the 2 plus da, 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 da. So every time I'm plugging in these k values in for my pieces, I end up getting zeros in the front every single time. Well, that's only true if this coefficient piece is always 0. Well, what does that mean? That means that k plus 1, c to the k, c of k plus 1 must be equal to negative ck. Or the next term in the sequence must be 1 over k plus 1. So let's list out a couple of these. I would then know if k equals 0, that means C1 must be equal to negative C0 over 1, or C1 must be equal to negative C0. If k equals 1, then C2 must be equal to negative C1 over 2. So C2 must be equal to negative 1/2 of C1, which is 1/2 of C naught. If k equals 2, then C3 must be negative C2 over 3. Well, that means that C3 must be negative C2. So negative 3 times 2 in the bottom, C naught. And these C's that I'm trying to figure out here, they're back in this solution. They're back. I'm trying to figure out what these are, okay? So I don't know what C naught is, but I do know that C1 is dependent on that, C2 is dependent on that, C3 is dependent on that, so on and so forth, and so on and so forth. And so if I were to keep going with this, my y, my solution curve, must be C naught x naught plus negative C naught x1 plus 1/2 C naught x squared plus negative 1 times 3 C naught x cubed. And I'm going to keep going on and on and on and on and on. I could factor out a C naught, and I would get that this is 1 minus x plus 1/2 x squared minus 1 over 3 factorial x cubed. And I'm sure you could try to figure out the pattern for that each and every time. Well, let's go ahead and try to figure that out. That's going to be C naught times, oh, we don't need that, the summation of, well, I need the sign to be alternating. So I need a negative 1 to the k. Let's make sure k is 0. Yes, 1. Okay, that's correct. It looks like I'm always over k factorial. And then x to the power of k. Well, if you go back to your Maclaurin series, this is just the opposite, or this is very similar to, I guess would be a better way to say it. It looks very similar to e to the x. The difference is e to the x is just x to the k over k factorial. But let's see, maybe I need to rewrite this. What if I rewrite it as negative x to the k over k factorial? So this is C naught times e to the negative x, right? Like if I plug in negative x here, that's what the solution is. And if you look back at how we did this with a linear integrating factor, look what we got, okay? So yes, this seems like a lot more complicated, but this is a very basic example of what you could do in order to figure out what these series solutions would be.